Okay, I think we can start. Yeah. Hello, everyone. Welcome to the AI talk. And today we are happy to have Yue in here to giving a talk about his recent research on the video understanding. The top title is Distinguished Vision Language Model on Millions of Videos. And the presenter Yue Zhao is a fourth-year PhD student at the University of Texas at Austin, supervised by Professor Phillips Cohambia. He obtained his MPhil degree for the Multimedia Laboratory at the Chinese University of Hong Kong, supervised by Professor Dahua Lin. More previously, he got his bachelor's degree from Tsinghua University. His current research interests are computer vision, particularly video analysis and understanding. And he's a recipient of the 2024 to 2025 NVIDIA fellowships. Okay, now welcome to Yue.
Okay, thanks, Kevin, for the introduction, and then thank you all for joining today's talk. It's my pleasure to be here, and then today I'm going to share some of the recent work on the video language understanding. Okay, so let's get started. So recently, we've seen this significant advance in vision language model, especially image language model. So starting from the very important work like CLIP, we've been able to see this kind of the power of image text pairs pre-training techniques. And then this has been applied to more advanced image-based vision language models, which can actually not only produce a single score, but also a fluent text description. For example, the COCA model, Flamingo, Party. And then there are also many works from the open source communities, for example, Unplug, Blip2, etc. All of these vision language models, I think one of the very important things behind of these models is the significant amount of pre-training data. For example, Google has this Webley 10 billion data, and then and then in the open source community, we have the Lion 5 billion, and then we have the even larger 12 billion data compound data set. So if but we don't kind of want to stop at understanding the images. So we want to basically have such capability for the videos as well. But how are we going to replicate such success for the video language models? So one of the key issues, I think, is because we don't have one of the reasons that we don't have the kind of the strong video language models might be that we are actually lacking such a kind of high quality video curated, human curated video text data. So there have been a few candidates to tackle this issue. For example, we can actually just ask people to annotate the videos, just like we annotate the images. But this has been shown to be very expensive. So there are some video dataset paper, and then they actually compute the time that is used to annotate a video compared to annotating a single image. And it turns out the annotation cost is actually 10 to 100 times compared to annotating a single image. So I think in this case, so it actually means that we might need to figure out some cheaper solutions to tackle this issue. So the other solution would be just leverage a strong image language baselines, because videos we can think of is as a sequence of images. So maybe we can just get some knowledge from the already strong sort of image language baselines, and then through fine tuning. So talking about fine tuning, so why do we ever need to fine tuning? So someone might ask this question. So why don't we just use a state of the art image based model and then just get the result out of it? So yeah, this is very straightforward. So let's have a example here. So here there's a man that is standing in front of a beach, and then there is sea behind him. And then we see this kind of man, the man doing a kind of sports, like some sort of martial arts. And then if we take the video as input and then cut it into a few frames, and then we see this kind of single frames, and then we feed it into an image caption model. For example, party in our case, and then we see the captions are actually pretty kind of not that satisfactory. So basically, we can see the man is standing. Of course, he is standing there, and then some in a particular shot that he's actually standing on one leg. But actually, the image caption model fails to describe the entire action of these in these examples particularly. So what about the other way? So maybe let's just get the video embedding, because we have strong sort of video model even without text, right? We can have the video embedding, and then we can compare with some like we can do retrieval. Basically, we have the embedding, and then we find the closest embedding from the image data set, and then we find the corresponding text, which is some way that is used to build up the video CC data set, so that we can get some alt text that is pretty much similar to the feature of such video. But as we can see here, so the result is still there's some issues. So basically, there's error in the alt text, because sometimes when we extract the feature might just be a bias to the context. For example, the man is in front of the beach, then the feature might be similar, but the alt text actually describing the man is balancing a surfboard. So, which is definitely not the case for the action that we want to know, right? So in this case, what we hope is something like this, right? So we give the frames, multiple frames, or like the video as input. We want to see the video caption actually describing something like a man that is practicing martial arts, or more in details. So for example, we want to see what does the man look like. So for example, the static appearance, sometimes we are more interested in this. Or sometimes we are more sort of interested in the detailed body movements. How does he perform such martial arts? Like, for example, we may hope the model is gonna produce like he's first standing, and then he move his hand, and then move his body. This kind of sequence of these description is something that we want. So that's why we want to adapt such model. So we want to fine tune this model. So in this paper, we actually introduced two techniques here. One is called video specific adaptation, and the other is called video instruction tuning. And then we propose these two techniques to sort of figure out this issue. So first is to adapt such model. So basically here is an image text model. The input is a pair of text and image, and then the text. So in a more general case, it can be think of as a instruction. So for caption, we can think of caption as a sort of a particular instruction that we human want the model to do, basically, which is to output a caption of the specific image. And the output is essentially another text sequence that is based on the instruction and the input text, input image. So for video language model, the input output is pretty much the same. Instead, the input is becoming a sequence of images, and then the text can still be some sort of instruction. So in the most basic form, it's like instruction that asks the model to generate the caption. So in this case, we have two stages. One is called visual adaptation, and the other is called language adaptation. So the key ideas here is that because the pre-trained image text model is basically pre-trained on only image and text paired data. So we want to adapt the visual part such that it can mitigate the discrepancy between the images and the videos, because the video may have some motion, and because of there's motion, there may be like a motion blur in it. So we want to sort of adapt this visual encoder to mitigate such gap. The other case is the language adaptation, which tries to enforce the model, try to give us more motion-specific descriptions. So in this case, we want the text that is that output by the model to describe the video in details and provide more diversity. So the first part is the visual adaptation. So in the visual adaptation stage, we only fine tune the video encoder, and then we freeze the language model, because the language model is totally frozen. So we actually don't care too much about the quality of these stages text quality. So actually any type of video caption data can be used here. So in our case, we use the spoken moments in time dataset, SMIT for short, because this is the largest video caption dataset we can find on the internet. So in this case, it's basically fine-tuning the video encoder. So after the video encoder is fine-tuned, we can froze the video encoder again, and then we try to fine-tune our language model part. So in this stage, because in the previous stage, as we mentioned, we only use a video caption dataset. So after in this stage, so even after this visual adaptation stage, the output is still some sort of captioning, because we always want the model to output some captioning data. So here in the language adaptation stage, we can inject more different sort of instructions so that the model is aware of what to answer based on different kinds of instructions, so that it will give different answers that is more than only the caption tasks that we do in the previous stages. So, but how can we get such kind of instruction data? So inspired by the LAVA, which is the visual instruction tuning paper for images, we do a very similar thing here to try to generate instruction following data for videos. So here we have a specific emphasis on the temporal reasoning abilities, because as we see here, for example, in this example, the person first is hanging in on top of some water, and then but he fails to hold his hand toward the rope, and then he just fell into the water. So this actually has a multiple stage in the video, and then we just want the model to able to be aware of such different stages of the video. So we can so during the prompting, we basically enforce the model to output such kind of instruction data that is more focused on the causal reasoning or the temporal reasoning of this particular video. And then the input, because in this case, we definitely cannot get something out of nothing. So we need these kind of original data that has this temporal or causal relation in the original captions. So, but for example, the spoken moments in time dataset, it's too short. It's just like 2 to 3 seconds. And then most of the captions is just like 10 to 20 words, which is just a sentence. And then we don't have this temporal relation at all. So we survey the entire literature, and then we find that video localized narratives is a dataset that is perfect for this case. So basically, they build up this dataset from a collection of multiple video data. For example, kinetics or UVO or like OOPS. So these videos are typically longer, for example, 10 seconds to 1 minute. And then because the videos are longer, so there are typically multiple shots or like different events happening in a single video. And then they ask people to densely narrate the video so that most of the video will have different events happening in time order, or there might be some there might be some course event happening, and then which leads to another event. So this will give us some foundation that we can build on top to get these causal reason or temporal reasoning data. So the prompt is very similar to the visual instruction tuning. And then if you have a chance to look at the data, I think it's very straightforward to just feed it into any type of existing large language model, and then to get the desired output. So here is a very interesting example that we can just see from the examples, and then see how the question and then the answer look like for the generated output. So in this case, the question can be served as some specific instruction. And then we can also come up with some other different kinds of instruction, whatever we want, so that all kinds of different capability can be included when we are constructing such kind of data set. So here's a quick wrap up. So basically, we have two stages to fine-tune our video language model from an image baseline. So basically, we first freeze the language part, and then we just adapt the visual so that we fine-tune on the video captioning data set, and then we just fine-tune the visual encoder. And in the second stage, we first build up this instruction following data set. Because this data set have some particularly, we have some requirement for the data because we wanted to have some detailedness. So in this case, we just use video localized narratives. It has 50K videos. And then for each video, we generate 10 pairs of such instruction and answer pairs. So this ends up to 500,000 data. And then we can mix it with the original caption data because we can think of a caption itself as a specific instruction itself. So, and then we have this mixed data, and then we can just fine-tune the language part while freezing the visual encoder. So that's pretty much the fine-tuning stage. And then after we have this model, and then we're gonna show some experimental result. Here, because we have, so we basically separate the experiments into two parts. One is because we want to measure how good is the captions. And then we have some experiment that illustrate the quality of the caption that is generated by our video language model. And the other is because we have this video language model itself, then why not just evaluate it and then see how it works in general case, because caption is something that it can do, and then it definitely can do something else. And then we want to see the generalization on a wide range of video language tasks. So that's two parts. So first is the harnessing the distilled captions. So here we basically look at the largest webless script videos that we can have. So we find video CC and then intern VID. So video CC has 7 million clips. That is script from 3 million different videos. And intern VID has a slightly bigger size, which is 10 million video clips from 10 million unique videos. And then we can apply our model on all videos that is in the data, and then we can train a script style dual-encoder model to on top of these video and captions. And then we are gonna compare the caption result, or like the captions quality, based on the video understanding performance of the pre-trained clip model. So here, first of all, we show the scalability of our of pre-training these kind of video model on top of the distilled captions. So we see that the blue curve here is the result that we feed into the clip model of using our video captions. And then we see a healthy improvement consistently when we scale the data from like 1% to 10% to the entire data. And then in comparison, we have orange curve, which is using image caption model plus a language model, which fills multiple frames result. And then we still see some scaling effect, but we see that scaling is not as good as the video caption that is generated from our method. And then we also have alt text baseline, because video CC is constructed by retrieving some image alt text. So we see that alt text actually doesn't scale at all. So this is basically, I think the reason behind this is there's compounding error of such textual noise. Because when we do the retrieval, there might be some spurious correlation of the visual similarity. And then because when we retrieve the alt text is from the image. So there is a significant gap between the images and then the videos itself. So here's the scalability. And then we can see the experiments that we do on other. So when we use the full data set, and then we can compare the clip model on multiple benchmarks. So here we compare the model on text to video retrieval on MSR-VTT and then the text data set. And then when we have such a clip model, we can also repurpose the kinetics model to the label. We can repurpose the labels into some text embedding, and then we can do zero-shot action classification on kinetics as well. And then we can see compared to the original data, both model that is captioning the video CC or the intern VID both outperforms the baseline, which is the original text. So here for intern VID, they already use some image caption model and then some LLM to summarize multiple frames captions. So this is very close to the second best baseline that we are comparing in these scalability experiments. And then we also put our method in context in comparison with other state-of-the-art methods. And then we see that the results can outperform the previous methods by quite a big margin. And then here we have another evaluation to show the generalization of our video language model. So we have not only we have the caption result because our model can do caption essentially. So we can also evaluate it on QA data sets, for example, MSR-VTT and then ActiveNet QA. And then we also have the next QA open-ended question answering benchmark. And it turns out like, so all of these comparisons are in zero shot, meaning that we just fine tune our model on the spoken moments, and next is the video localized narratives. And then it never sees all these data sets, MSR-VTT or ActiveNet. And then we can see that our video language model can outperform either the state-of-the-art or the image party model by quite a large margin on most of the benchmarks. And here's a few ablations. For example, we see both the visual adaptation and then the language adaptation will contribute to the final retrieval result. So we just, here there's a two-stage happening here. So we just have one stage of fine-tuning, and then we use the fine-tuned model to generate the captions, and then we use the caption to do the clip pre-training so that we can measure the zero-shot performance here. So this is actually a kind of a second stage pre-training to show the first stage's effect. And then we also compare, because here we are very close to the visual instruction tuning method. So we actually show that it is very important to use a video data set to do video-specific instruction tuning. Because we show that if we use image instruction tuning data set, actually the performance on the video data is not as good as our case. Okay, so here's some visualization result, which we show the image captions model and then the original alt text, and then our method that is adapted in two stages. So we can see that our model can actually produce much more detailed descriptions compared to either the image caption or the image caption plus the large language model summarization. Because in most of the cases, if the image caption cannot lose the information from the, for example, the motion or the action, then there's no way that the language model that can restore from the image captions unless it hallucinates. And then there's definitely a lot of like factual error if it tries to hallucinate such motions, which actually we don't want it. So here's another visualization result. So I'm gonna just skip it very quickly. And then, so that's it for this paper. And then there is some broader impacts of this method. So we have some follow-up, which shows that actually this method can nicely scale to 100 million scale videos. And then this has been implemented to support the video prism, which just came yesterday. So we have, which is a generic video encoder that nicely combines both video text contrastive learning and mask video modeling. And then it also outperforms on a very wide range of video tasks. I just put the archive link here, so if you're interested, feel free to check it out. Okay, so we have these great methods, but here's some bigger challenges. So what's the big challenges? So think about this. So we have millions of video text pairs. And then if we look at the text, so millions of texts will end up with kind of less than billion scale tokens, definitely. So if we just put it on our disk, so that's only several gigabytes. So which can even just be put onto our RAM of any kind of laptop, right? But if we look at the video size of these million scales of videos, this is actually more than 10 terabytes. So here I already use a resized version, which is like, for example, 320 pixels on the edge, which is not the like 1080p, the high resolution videos. So these videos are actually 1,000 or even 10,000 bigger than the text. So this definitely gives us a huge challenge on how we're gonna load these kind of video data to efficiently train the video language model. And the other bigger challenge is essentially the memory footprint. As we know that our model takes the video, which is a sequence of images as input. So the sample right now is not a single frames. Instead, it's each video is gonna be several frames. So the per sample memory footprint is actually significantly increased. So in other words, so the batch size that we can feed in each GPU actually significantly reduces, right? So that means that for most of the cases, we always want to launch we also want to use a cluster of GPU or TPU servers to run a single job, which is very hard to find such resources in the academia. So are we gonna like give it up or like just let the industry train video language models? So we want to find some ways to mitigate such gap because we don't have such kind of resources. So here's the thing. So if we look at the footprint of a video VIIT model, actually we realize that most of the memory bottlenecks can be avoided. So here's a profile of a VIIT model that is mostly like layer norm and then multi-head attention and then the MLP layers. And then we see that if we use the recent proposed memory efficient operations, for example, flash attention, we can actually just get rid of these attention weight. So we just have the layer norm and then the MLP's parameters. And then if we have some more advanced techniques, for example, gradient checkpointing, we can actually reduce the memory footprint significantly. So in this case, if we just apply a vanilla VIT, which is not the transformer that we typically use in previous experiments, we see that once we have these techniques inside, the memory footprints of vanilla VIT actually is much more higher than the, is much more smaller than the transformer, which means that the maximum batch size that we can have on the vanilla VIT is actually much larger than the transformer because the transformer, they have these separable spatial attention and then the temporal attention. So actually the parameter is, we can closely think of it as doubled. So this also leads to because of the memory efficient attention, so the training throughput can actually be increased compared to the transformer baseline. So here, so we figure out the memory footprint. So how about the I/O bottleneck? So here's another issue that we just realized. So when we are loading the long videos, we are loading an entire long video into the RAM, and then we just try to decode only a few frames out of it. And then most of the bandwidth is actually wasted. For example, here as an example from the Eagle 4D dataset. So the average length for Eagle 4D data is typically like 20 minutes on average. So that means each video we're gonna take 100 megabytes. So that is very large. So I already resized it to be 20 pixels on the shorter edge. And then, but when we train the model, we only just take a few frames out of it. So what we're gonna do, so here we have a very tiny tricks here, which is try to split the entire video into a few chunks. So the chunk is actually determined, the chunk length is actually determined by this formula. So basically, for each iteration, when the model is running, the network disk can actually give you some bandwidth. So which is we can say it's SR, which is the maximum read speed that can support from the network system or like your local system if you're just training on your local machines. And this delta times SR should be greater than this B times rho times T. So what is B? B here is the batch size of the videos that you're gonna load in this step. And then the rho is the average bit rate of the video, and then you can have a very accurate approximate out of it because this is just based on how many pixels there are in your video. And then the T is the optimal time. As long as the T is shorter than such scale, then we can just get rid of the IO bottleneck. And what else? So think about when we are loading from these videos, there is video encoding and then decoding things happening here. So when we are loading from the videos, we first need to decode the video. And then after decoded, we have like a decoded tensor. And then we apply the video related augmentations, for example, random resize crop, and then these color jittering, you name it. But these, both the decoding and then the, for example, cropping based augmentation, both of these are very CPU intense operations. And then, so here's an idea. So why not we just fuse both the decoding and then the cropping? Because some of the pixel we just don't want it. When we decode it, why not just ask our video decoder to just get rid of those things and then just give the perfect position that we want. So here comes our approach, which is fused decode augmentation. We call it a fused decode crop. We basically just rewrite the cropping operations as a filter when we are calling the FFmpeg video reader. So as we see from this toy example, so here is illustration. So we actually didn't run any model here. So we just launch a few video loaders in parallel. And then we just see the processing time of each per video when we are launching these different processes in parallel. We can see that once we fuse the model, we can get a close to linear scaling of such throughput when we compare to we first decode the video and then cropping the video. So this actually can save a lot from especially when we don't have a very strong CPU and then it needs to switch between decoding and then cropping or even other, especially when you have a series of croppings based augmentations, this can be very time consuming. But here actually it turns out that we can merge all of it into a single stage. So these are basically the three steps. We have our memory efficient architecture. We have the IO loading from just short chunks instead of the entire video. And then we have the fused operators that first that do the decoding and then cropping simultaneously. And then we can show that our pipeline here can train a video language model much more efficiently. So here's the illustration. We show that we are able to train a video language model on Eagle 4D. So because this paper is actually done before the VIIT paper, so we at that time we just have Eagle 4D to test out our method. We see it used cheaper hardware, which is like NVIDIA A5000, which is slower and then much cheaper than the A100 or like V100 machines. The total amount of GPU hours and then the carbon footprints are significantly reduced. And then because in our case, it turns out we can afford a significantly larger batch size on a single GPUs, and then so this will lead to better zero-shot results. So this is probably because of the large batch size that is going to support in our new pipeline. So, and then the better pre-training model actually generalizes well on downstream tasks. So we show that the Eagle 4D pre-trained model can show pretty good performance on application multiple instance retrieval and action recognition tasks compared to the baseline. And then this also won the last year's Epic Kitchen challenges in video retrieval and then video recognition. Okay, so what else? So we also have the video mask auto-encoder model, which is another type of very popular video modeling techniques. So it turns out like our pipeline can also exhibit the video MAE training because we have these masked video tokens when we are training the video MAE. So actually, the model can afford a very large batch size, which means at each iteration, we need to read a lot of videos. So that gives us a huge data I/O bottleneck. And then we can apply the fused loading techniques in the video MAE training as well. And then here's the data loading overhead and then the training speed curve. And then we can see that the fused decode crop can significantly reduce both the data loading overhead and then improve the training speed compared to the original paradigm, which is first decode and then crop. Okay, so and then to sum up, so training a video MAE can actually takes 40% less GPU hours without losing any accuracy because we didn't touch the model at all. We just improved the data loading part. And then this pipeline is more efficient for the video MAE task. Okay, so here's basically a summary of the papers that I just mentioned in the talk. So, and then for the efficient training and then the La Villa baseline, both of the papers has already been open sourced. And feel free if you want to check it out and have a try. And then that's it from my end. And thank you for joining, and I'm happy to take questions.